Oxidation reduction reactions are a class of reactions in which electrons change which atom they are associated with. And since oxidation reduction is kind of a lot to say, they're often abbreviated as redox reactions. And oxidation reduction reactions include many very common types of reactions that have other names, such as combustion reactions, are oxidation reduction reactions. Also, any that form compounds. And these are just a couple types of reactions that are oxidation reduction reactions. All right, so if electrons change atoms, then in order for a charge overall to remain the same, something has to lose electrons, and that is known as the oxidation part of the reaction. Oxidation is losing electrons. An example would be sodium turning into sodium plus, and of course that involves the loss of an electron. So when sodium becomes sodium plus and loses an electron, that's oxidation. The sodium lost an electron and was oxidized. The other half is reduction, which is gaining an electron. An example of that would be chlorine gets an electron and becomes chloride anion. Okay, and technically chlorine doesn't come as a single atom. It generally comes as the diatomic, so we'll take half of one chlorine diatomic plus an electron and say that it makes Cl- in order to start with the natural form of chlorine. Okay, so then we can combine an oxidation half reaction and a reduction half reaction into a regular reaction. Sodium plus 1/2 of the chlorine makes sodium chloride. So when you combine those together, you say that sodium got oxidized because it lost an electron, as we showed up here. But the really confusing part of it is we also say that sodium acted to reduce the chlorine. Okay, so the chlorine got reduced, but we say it was reduced by the sodium, which got oxidized. So we say that the sodium is also the reducing agent. So it got oxidized, but it was the reducing agent. It was the agent that caused the reduction of chlorine. Likewise, we say that chlorine, while it got reduced, acted as the oxidizing agent. So it was the agent that caused the oxidation of the sodium. This is a very confusing terminology, but it is used, so you would need to learn this. All right, and so this is an example of oxidation and reduction in an ionic compound formation reaction. Remember we said above, one type of redox was compound formation. So if you start with elements and turn it into a compound, that is a redox reaction. Another type of reaction can involve molecular species, covalently bonded species, such as hydrogen and chlorine. Okay, because when you form HCl from hydrogen and chlorine, and of course you'd have to form two of them if you started with 2 hydrogens and 2 chlorines, we say that there is a dipole in the species. The hydrogen part is partially positive and the chlorine part is partially negative. So hydrogen was neutral when it started because hydrogen will share electrons equally with itself. Chlorine will share electrons equally with itself. So the hydrogen became partially positive from neutral, which is oxidation. Okay, it lost some electrons, it became more positive. Even if it didn't fully lose an electron, it lost some electron density. The chlorine, which started neutral, became slightly negative, which means it gained some electron density. So we also say that oxidation reduction occurs in covalent compounds. So the hydrogen got oxidized, and therefore also was the reducing agent. And the chlorine got reduced, okay, it became more negative, and so it was also the oxidizing agent. All right, now in order to keep track of this moving of electrons, we use a system called oxidation numbers. And when we do this, we assign a number to various compounds. So it is going to be an integer, which means it can be positive or negative. And they are integers assigned to each atom. To keep track of charge. And really charge movement. Okay, so for ionic compounds, the charge on the ion is simply the oxidation number. And this is for single atoms that are ions. So the charge on the ion is going to equal the sum of the oxidation numbers for the parts. All right, so this can refer to a single atomic ion or even a complex of atomic ions. Okay, so for covalent compounds, the oxidation number will be the charge that would be the case if the electrons were completely transferred and not just shared. Okay, so if they were not shared but they were completely transferred, then the number corresponds to that oxidation number. All right, let's do some examples. That'll make it a lot easier. All right, so for pure elements, the oxidation number will always equal 0. Okay, no matter how many are involved in the pure elements, like potassium, solid potassium, oxidation number is 0. Hydrogen, it comes as a diatomic, the oxidation number is 0. Chlorine comes as a diatomic, oxidation number is 0. And for neutral compounds, such as CO2, NaCl, or even something with lots more atoms, the total oxidation numbers for all atoms sum to 0, okay, for neutral species. If you have ions, whether they have more than one part in them or not, the oxidation number will sum to the charge. Okay, so like sodium plus, the oxidation number is just the charge, +1. But for NH4 plus, which is not a single atom, atomic ion, the total oxidation numbers for the nitrogen and the 4 hydrogens has to sum to +1, has to sum to the charge. Something like sulfate, the oxidation number of the sulfur and 4 times the oxidation number of the oxygen has to sum to -2. All right, and some specifics that you should just learn are group 1A elements will always have a +1 oxidation number. Group 2A will always have +2 when they're in compounds, okay, not when they're by themselves. Pure elements will always be 0. Hydrogen will almost always have a +1. There are exceptions. It will be -1 when it's with metals or boron. All right, fluorine is always going to have a oxidation number of -1. The other halogens will almost always have, likewise, oxidation number of -1, but when they are with other halogens, they may not, or with oxygen. Okay, so except with oxygen or halogens, and actually higher halogens. And by higher, I mean higher on the periodic table. Okay, so when with oxygen or higher halogens, they will have something other than -1. Otherwise, it will always be -1. Oxygen will have a oxidation number of -2 almost always, except when it's with when there's 2 oxygens in a row. It'll be -1 for an oxygen-oxygen bond, and it won't be -2 when it's with fluorine. It'll be something else. All right, so those are some guidelines that you need to remember. Remember these specifics, and then we can talk about some examples of assigning oxidation numbers. All right, so let's do a few of these. If we look at magnesium fluoride, this is an example where both parts of this species are on the list. Magnesium is a +2 because it's in group 2. Fluorine is always -1. And since there are 2 of them, that makes a -2 overall for the fluorine, which will completely balance the +2 for magnesium, and which is what it should do because it's a neutral species. Okay, so these are both on the list. So whenever you have both on the list, you can simply assign the numbers. Okay, HCl is also on the list. Hydrogen is going to be +1, except under certain circumstances that this doesn't include. And chlorine is going to be -1, except for when it's with higher halogens or oxygen, and it's not. So they totaled 0, which is the charge on HCl. All makes sense. Okay, but sometimes you will know the oxidation numbers of some parts and not others, and you have to deduce one. So here are some examples where you have to deduce one species. So we look at scandium 2O3. And we know scandium's not on the list. Okay, scandium is not on the list, but oxygen is. Oxygen is -2. And since there are 3 of them, then that means oxygen totally it counts for -6 for this species. And since it's neutral overall, it's not charged, that means this scandium part has to be -6. And since there's 2 of them, that means they each contribute a +3. So we can deduce the oxidation number on scandium by knowing oxygen and knowing that it's neutral overall. Let's do another example. Here's our first example where it's not neutral overall. You have a -2 charge, so it has to total -2. Okay, what do we know here? We know hydrogen is going to be +1. We know that oxygen is going to be -2. We don't have phosphorus on the list, but we can deduce it because we know the others and we know the charge. Okay, so we have 4 oxygens at -2, so that's -8. We add 1 for the hydrogen, which is -7. We want -2 overall, so we need a +5 in the phosphorus in order to add to -2. So 4 times, so you can write it as an equation. You can write +1 plus, and I'm going to write it as +5 plus 4 times -2 has to equal -2, the overall charge. Okay, so if you didn't know one of these, you could solve for it. You could, before you knew what phosphorus was, you could have put an X here, and so you could have then solved for it. Okay, continuing on. This is a case where we know fluoride is -1, it's always -1, and the other halogens are -1, but not when they're with a higher halogen on the list, and here we are with a higher one. So in this case, we have to deduce what iodine is. Okay, we have 3 fluorines. So our little equation, let's say this is X. The oxidation number for I is X. We say X plus 3 times -1 has got to equal 0, because the overall charge is 0. There's no charge there. And then you can solve for X, and X will equal +3. So then we know that this one is positive 3. Okay, let's do some more. Here's one where you know oxygen, you don't know sulfur. Let's write our little equation. We can call this X. We can call this, and we know that oxygen is negative 2. So we can say X plus 3 times negative 2 has to equal the overall charge, which is 0. So we know X equals positive 6 for sulfur. All right, you should try some of these then before you watch me do it. So we have a few more on the page, and you should try them, and I will go through them as well. All right, ammonium dichromate. Lots and lots of atoms here. So we need to realize that all these together need to add to 0. It's not charged. We could also keep in mind that if we know this is a polyatomic ion that has a charge of +1, and we know this is a polyatomic ion with a charge of -2, we could do them separately with their summing to their own charges, and you'd get the same answer. So either way is fine. I'm going to do the total way, or no, I'm not going to do the total way. I'm going to do the partial way, because we don't know chromium. We don't know chromium, and we don't know nitrogen. So we have 2 unknowns. We can't do it all at once. So we're going to have to do NH4 plus by itself. And the fact that there's 2 of them will not affect the oxidation number assignment. All right, so hydrogen is +1. We have 4 of those. That makes +4. We need +1, so we need a -3 for the nitrogen. Now the dichromate, and that'll be true for both the ammoniums. Then the dichromate, Cr2O7 2-, we can do by summing up with an X if we want to. You can do it in your head, or you can do it with an X. Oxygen is -2. So you have X plus 7 times -2 is going to have to equal -2. So your X is going to turn out to be positive 6 for chromium. All right, aluminum sulfate. Again, well, aluminum you can pretty much guess, because the aluminum is a 3+ charge. And even though it's not in our list, anything that is a single atom with a charge is going to be that, the oxidation number is going to be that charge. So aluminum is going to be +3. And sulfate we can do separately if we want, knowing that sulfate is a 2- ion. Or you could deduce it by saying there's 2 aluminums. Either way is correct. But let's do it this way. We'll say we have X. We have -2 for oxygen. There's 4 of them. So we have X plus 4 times -2 equals -2. Sulfur will get a positive 6. Sulfuric acid is going to be much the same as we got up here, because there is a sulfate in there. And once you've figured it out for sulfate, you don't have to redo it for another sulfate. This is a sulfate in here. Hydrogen gets +1. Sulfate is always going to have a sulfur with a +6 and an oxygen with a -2. You can just write them down. And finally, 2 neutral species, 0 and 0. Now that we've learned to assign oxidation numbers for individual species, we can use that information to look at an entire reaction. So we have this reaction, aluminum reacting with sulfuric acid to form aluminum sulfate and hydrogen. And we want to know what is oxidized in here, what is reduced. The way to figure that out is assign oxidation numbers for everything there and see what changes. All right, we just did all these species on the last page, so I can just transfer them. Aluminum was 0, hydrogen was 0. We had a +1 for hydrogen, we had +6 for sulfur, we had -2 for oxygen, +3 for this aluminum, again +6, -2, and we're done. Okay, they go to the elements. So oxygen is -2, sulfur is +6, etc., etc. And then look at what changes. What elements change oxidation number. All right, so let's look at which ones change. You may notice aluminum went from 0 to +3. It changed 0 to +3. Then you say, is that an oxidation or a reduction? Well, it lost electrons. It becomes more positive, so it is oxidized. And we can also say that aluminum is the reducing agent. What else changed? Okay, did sulfur change? No. +6 to +6. Oxygen, -2 to -2. Hydrogen went from +1 to 0. Whenever you have a redox reaction, you have to have at least one thing that oxidizes and one thing that reduces. Okay, so hydrogen goes from +1 to 0. That is gaining electrons. So that is reduced. And hydrogen is then, or you can say then that actually sulfuric acid is a reducing agent. Some people say that the hydrogen itself is. Some people say that the whole species is. So we'll say the whole species is the oxidizing agent. But it's the hydrogen part of it. Okay, so here is, I want you to realize that not all reactions are redox. Okay, in many reactions, the oxidation numbers do not change. And here's one. Zinc chloride plus copper hydroxide going to zinc hydroxide plus copper chloride. Okay, if you go through and assign oxidation numbers to all these, you'll find zinc is +2 here and it's +2 here. And if you go through all of them, they'll all be the same on either side. It's not a redox reaction. Okay, so what is the strategy? The strategy is you assign oxidation numbers, and then you can see what changes and decide what's oxidized and what's reduced. So here's one for you to try. Okay, so let's assign oxidation numbers. Carbon monoxide, the two together need to add to 0, and we know that oxygen is -2, therefore carbon has to be +2. I2O5, oxygen is -2. There's 10 of them, which means that this needs to make +10, which means they're each +5. This iodine is a neutral species, just an element, so it's going to be 0. And here, carbon dioxide, -2 for oxygen, but now there's 2 of them, which is -4 charge. So this needs to have a +4 charge. Then look at what's changed. The carbon went from +2 to +4. That's an oxidation. So it was oxidized. The other thing that changed was iodine. Went from +5 to 0 when the reaction occurred, so it was reduced.